Hello again, welcome to my channel, and today we're going to have a look at transistors. So first of all, what does a transistor look like? Well, the most popular ones are these two types of transistors. You can see that the black plastic encapsulated one and the metal can. Now if you notice, they have three legs, and we've got to be able to identify these legs. So we'd look up the number on there and the data sheet. And the names of the three conductors are the collector, the base and emitter. And we have to know which one of these is which, so we can get it to work properly in the circuit. It's the plastic one. Now the metal canned one, it's a little bit easier with these because they've got a tag on them. I don't know if you can see there, they've got a little metal tag underneath. And the closest one to the metal tag is the emitter. And then if we go clockwise around the transistor, we've got a base, and then the third leg is the collector. So these are really tiny devices. Now the devices that these replaced were these, which are thermionic valves. If you've ever heard the term old valve radio or a valve TV, these are the guys that used to drive it. Now they're ridiculously inefficient because they worked on the principle of thermionic emission. And therefore they had to have heaters in them, so you had to supply the heater as well as the rest of the connections on the component. And of course they got very hot, they were very unreliable. So when you got a transistor that came in to replace it, they were cold, they're far more efficient. And because these are semiconductor devices, they take a lot less energy, they're solid state, so they are far more reliable. As I mentioned, they're semiconductor devices, so that means that you can actually etch these onto silicon wafers, or inside it is silicon wafer technology. But of course you can literally etch hundreds or thousands of these onto a chip to make a silicon chip. So instead of having a circuit run by these, which you need an old room to give you the processing power of a desktop calculator, you can put thousands of them on a chip and have a scientific calculator, which is really small. If we have a look now how a transistor behaves in a circuit. Okay, so if we have a look at a circuit now with a transistor in it, what we have a power supply there, and then we have this variable resistor, and that is then going through this other resistor feeding the base of the transistor. And this transistor is driving this second LED here. An important thing to notice is this LED is a lot brighter than the other LEDs. So if you can keep that in mind for a second. So you might say, well, why do you want to drive that with a transistor when you can easily just rig up a resistor and an LED and drive it through there? Well, it's to show you that this can be replaced by things like motors and things like that. And the reason that this LED is a lot dimmer, because that is showing you the base current. And the base current is tiny, whereas you have a substantially larger current flowing through the collector emitter, which is what this diode is showing you. Now if I turn off the current to the base, you can see the device turns off. And I'll just reconnect the base of the transistor and then it turns on. The base is like a tap. So if you put a small current into the base, it controls this large current through here. Just like turning a tap controls the flow of water, that base current is controlling the current that's running through that transistor and powering that LED. Now, because it's such a small current, it's easily to control. And so I can control the base current. I can turn it up a little bit. And as you see, the base current is rising. So consequently, the emitter collector current is rising as well in proportion to it. And that's magnifying it quite a bit. And that magnification is called gain. So that's a very important term to use, is gain in these in transistor circuits. So transistors actually have two applications. You can use them as a switch to switch things on and off. So you saturate them and cut them off. So that gives you the two ends of the spectrum. And somewhere in between that, when we look at something called a load line, which we look at in the future, you can use it as an amplifier. So you can put a tiny signal into the base, and then that gets magnified and the collector emitter current reflects that, but a lot bigger. It gives you a lot more gain, so it magnifies that current substantially. So the two resistors in here, then this resistor is just controlling the current through the base. That the variable resistor is just added in to give you that little tweakability in control, but this is protecting the base from an overload current, and this resistor is just controlling the current through that LED to make sure that the full 9 volts of the supply doesn't go across that LED, because otherwise it would just burn it out instantaneously. Okay, so that's the circuit. So just to summarize, small current running through the base controls a large collector emitter current. So let's have a look at some diagrams to show us transistors. Okay, so we mentioned the transistor was a silicon device, silicon based, and here we are. If you remember, when we looked at diodes, you had a p-n junction. So with the transistor now, it's actually got 3 layers. So you've got the collector, the base, and the emitter, and whatever material they use to sandwich them dictates what kind of transistor it is. So it's an NPN transistor or a PNP. If you remember, the diodes just has a P or an N type material, but this has the sandwich of the 3. If you look at the symbol for the transistor, this here we've got the collector, we've got the base, and we've got the emitter. Now on an NPN transistor, the emitter arrow points outwards at the end. On a PNP transistor, the emitter arrow points inwards to effectively into the base. So that's how you tell the difference between the two. So semiconductor materials in a sandwich, and then the two symbols corresponding to those. So next, let's have a look at the currents and voltages and what we call them in the transistor. Looking at the currents and the voltages in the transistor, you've got first of all the I collector. So you use the collector current, and then the I emitter, and then you've got the base current going in. So that's IB. Capital letters because the transistor is off load, so they all use uppercase letters. So as we've said earlier, the base current is really small, sort of milliamps, compared to the current that is flowing through the collector emitter. You have the voltage collector emitter there, and then the voltage base emitter. Now that's quite important. Now if you remember when we looked at diodes, the diode wouldn't work until we crossed the threshold of 0.6 volts. And that's the same here, because it is a semiconductor sandwich. Again, this VBE is always going to be in the order of about 0.6 volts, particularly for silicon transistors. 0.6 volts voltage base emitter. If we have a look at how we connect in the transistor to a circuit to get it to work, if you remember when we talked about diodes, when we forward biased the diode, the N was connected to the negative and the P-type material was connected to the positive, and we had conduction. And then we had reverse bias where the N was connected to the P-type and the P-type was connected to the N-type. That was reverse bias, so we had no conduction. So when we connect up a transistor, we've got to bias it properly to get it to work, or otherwise it's not going to work at all. That's why it's so important that we know which connections are which on it. Now this is an NPN transistor, so we've got an N-type material on the collector, a P-type on the base, and an N-type material on the emitter. So the P is connected to the positive and the N is connected to the negative, so that means that the base emitter junction here is forward bias. If we now look at the base collector junction, we reverse bias the base collector junction. So the base emitter is forward bias and the base collector is always reverse bias, and then we can get conduction in our transistor. If we have a look at this circuit here, is the LED circuit we saw working a little bit earlier. So we've got the collector emitter current there going down to this diode that we power in, the LED there. And if you look at it, this 470 ohm resistor is just protecting this diode. But if you look at the base, we've got a 10,000 ohm resistor. So giving us a tiny current into the base to make the transistor work. And we can see for this formula here, I emitter, so the current that is coming out of this emitter is equal to the I base plus I collector. So you've got the two currents flowing down here, and then all the current then will come out of the emitter. So that's how it works. You've got a tiny current switching this transistor here to allow this larger current flow through it. When we're using it as an amplifier, it would be an exact reproduction of that, just bigger because of the transistor gain. But here we're just using it to control this little LED. So that's a basic summary of how a transistor operates. It can be a switch or an amplifier, and as you've seen in the circuits, we've seen how the transistor behaves. I hope to in the future do another video on transistor amplification. So until next time, thank you very much.